Okay, good morning. We're going to continue with neural networks today. So I know that at least one of you is asking for the data for the thing, and I've posted half of that. I posted the weights you should use, and I'll post the out. Try that. Thank you. Okay, back to where we were. So how many of you think that you've got the feed-forward network mostly coded? A handful of you. So keep working on that. The feed-forward is pretty straightforward, in quotes. Nothing is straightforward until you figure it out. But after you figure it out, everything's obvious. Yes?
How many nodes per layer are we supposed to have in each of our format layers?
Okay, so the question is how many nodes per layer? And see if I can get this thing working. It depends. The number of input nodes is how many features you have. So for you guys, that answer is 8. The number of output nodes depends on how you code your output, but if we're doing it with one hot, it's the number of classes. How many classes do you have? 10. So you've got 10 outputs. The number of hidden nodes is arbitrary. We'll talk some about that later today. For the homework assignment, pick 4. I think I told you 4. Just because you need something to code until you get to through today's lecture and thinking about the actual project itself.
How many summations?
You're going to have one summation per node. So you're going to have a summation, one summation for this. If you've got 4 hidden, you're going to have 4 summations here. If you've got 10 out, you're going to have 10 summations here. And this summation is going to sum 8 weights, inputs times 8 weights. This summation has 8 things going into it. This has 8 going into it. This has 8 going into it. This has 8 going into it.
Yeah, so I don't think it needs the right terminology.
Okay.
So there's 4 summations in the first hidden node there.
Right?
Then our 4 hidden nodes, do we want 4 summations?
Each hidden node has one summation.
So just do that.
This is one hidden node. This is one hidden node. This is one hidden node. This is one hidden node.
Oh, okay. So I was looking at it vertically as 1, and we want.
We have one hidden layer.
Yeah.
One hidden layer with 4 nodes. We have one input layer with 8 inputs. We have one output layer, which is going to have 10 for your project output, 10 nodes. That better? Other questions that have come up. And again, the reason I gave you homework 5 is because I've seen in the past students, when I give them the whole project, they can't make any progress. And if you can't go forward, then you can't go backwards. So I want to see if you can get the feed forward, which should, if you've been coding it, you should say it's not that hard to do. It's not that hard to code the feed forward. But if you can't code it, you can't do the rest. Remington.
So from a question, will that be before or after?
At this point, after. I don't think it's reasonable for you to do it before.
And will you still be available in email or some format
in some form over spring break. Tentatively, our plans are to take my camper in the Southwest someplace and go hiking. So on days when I'm hiking, I will not be available most likely. I don't think there's going to be cell towers in certain places. But on days when I'm not hiking, if we are anywhere that has cell service, I will have limited access. And will be willing to answer you at certain times. My boyfriend will be very upset if I spend all day on the computer during spring break. As it is, he's upset when I spend all day on the computer on a weekday, non-spring break. So, okay. So try to get the feed forward coded. I'm giving you, and I've already put up on Blackboard, the values for these weights and the values for these weights. How many weights are here?
How many
Weights. 32, 8 by 4. And I think I saved it as a 4 by 8 matrix. Because technically, look at these letters here, it's WJI. J is the number of hidden nodes, it's the index for your hidden nodes. I is the index for your inputs. So this is WJI, so it's saved as a 4 by 8 text file. Has no headers to it, no labels. It's just, excuse me, raw data, which hopefully makes it easier for you to read it in and just plug it in to a variable someplace. Yes.
So this, for YJ and ZK, those green boxes, that's the activation. Are those the activation functions? Are those where we get?
Yes, these shaded boxes are each an activation function.
So we don't use the activation function on the.
No. The activation functions follow summations. And again, that's why I've come up with this homework 5, is to try and help you guys get things put together before you get into the complicated stuff of the whole network. Please keep asking those questions so you can get the big picture of how the stuff's put together. It's a lot more obvious to me than it is to you. I'm trying to help to make sure that we can get this through to you. Other questions that have come up?
So for the weight, we are guessing that we take the J node, we take the J hidden node, and multiply by each one of those XI, and we'll multiply by the weights.
Yes, we're going to take this input times this weight, which is weight 1, 1. We're going to take this input, multiply it by this weight, which is weight 1, 2. We're going to take the third input, multiply it by this weight, which is weight 3, 1, because we're going to the first summation. How many weights are here? 4 by 10, or really, K's first. K is your output, so 10 by 4. Mm-hmm. It's the way that the community has built it. We're not going to buck the community. Part of your goal is to be able to join the community and communicate with the community. So you need to use the terminology that they use.
So like you call it a hidden node, in the coding, we just basically take the output, multiply by the second.
You're going to feed forward You can take your inputs, multiply by weights to get net j. Take net j's, put them through your activation function to get yj. Take your yj's, multiply them by weights, and add them up to get net k. Take your net k, put it through an activation function to get zk's. And then eventually you're going to compare your zk to your tk when we get beyond homework 5. For homework 5, don't worry about what values come out for zk. They're just kind of random values. Just to see if you can get the coding to get the right math, that you've got the whole thing structured right. Correct. It doesn't have to be in a broad sense. For now, I want you to make this activation function equal to this one. So you're going to have 4 the same and 10 the same. And I told you what function to use. Just because I told you what function to use. In theory, you set that up as a function in code that you can change. You put in a scalar, you get a scalar out. You put a vector in, you get a vector out. Figure out how you want to code it. You can code this as one step if you can do a function of a vector. You can code it in a for loop with 4 individual steps. I don't care, it's your code. Likewise, what's the coding simplicity for this step? Louder, you're right. Matrix multiplication. Your xi times your wji, or really wji times xi. So you can accomplish net j is equal to the product of these two in one step if you can do matrix multiplication in your code. If you can't, for loops work fine. There's nothing wrong with a for loop, make it nice and neat and pretty, but you could do it with matrix multiplication depending on how you like to code. Your choice, your code. You write neat code, things go better. You write ugly code, you live with it. I think you're figuring this out in the earlier projects. How many of you had some pain because of suboptimal coding decisions? However, that's the only way you learn to write better code. And learning to code well is a good skill. Employers will really appreciate that. You'll be able to sell yourself that much better. Other questions? Any questions from home? No questions from home. Okay, so we're going to assume at this point that you can feed data forward. If you can give it 8 inputs, you can calculate 10 outputs. We're going to make that assumption that at this point, you can do that. And by Thursday, when you get the homework done, we'll kind of have proved that you can do that. So does that mean you have a classifier? No. What's missing? Gradient descent to accomplish what? What do you want to, what does back propagation accomplish? Updating weights. You want to choose the right weights. I'm giving you random weights, literally generated by a random number generator. So with random weights, this is not a classifier. If you get good weights, then you have a classifier. Right now, you've got a network. It is not a classifier. So we need to do the next step, which is adjusting the weights, finding, in quotes, optimal weights. And been throwing out good buzzwords in the classroom here: gradient descent, back propagation. Those, excuse me, are techniques used to determine good weights that determine and make a classifier. So right now you do not have a classifier. Homework 5 does not build you a classifier. Builds you a random network. Lets you do some experiments and just running numbers, but nothing makes any sense. So the next thing is, how do we train that network? We want to train that network, and that training is adjusting these weights so that when you put in features that are connected to a class, you will get output values that tell you what class it is. And ideally, we're going to come up with this target value, which is what you want them to look like. So you're going to come up with a secret code that says TK, which is a vector, it's a range of numbers, has this pattern if it's an A, has this pattern if it's a C, has this pattern if it's an E, etc. And if you do it right, ZK, if your weights are correct, ZK will be equal to TK. If you've trained it, and it's going to be, ZK is going to be equal to TK for every input. So whenever you give it features that match an A, you should get ZKs that are equal to whatever your code is, say A. And if you put in features that go to a C, you're going to get ZK that match your TK that say C. That your weights learn your secret code. Same thing for 3-layer. Want to go over the variables we've got here? Your inputs are either called I for input or X. The problem with I is we also use it as our subscript, our index, so we tend to use X a little bit more frequently. Outputs, O for output, or Z, because we're going to have the X, Y, Z. Target values, T for target values. What we want, those things. What's our secret code for A? What's our secret code for C? The output of the summations we call net. You've heard of net profit, net income. It's an accumulation of all those pieces there. So the output of each of these summations, is a net. And if it's the first hidden layer, it's J because we're counting J's there. Second one would be K's, which might be an output if you stop after 2 layers. L if you need to go further. If we were to build a 4-layer network, we might have M. Aren't we exciting? Okay, same procedure. And if we had a 5-layer network, you guys are so brilliant. Okay, so we just keep going the next one. And then we've got weight matrices. And these are backwards. That one's correct. We tend to write them in the opposite direction. Partly so that we can do the matrix multiply with a vector, column vector. And so we've got the first set of weights, second set of weights, third set of weights. If we have a 3-layer network, we have a third set. If we had a 4th layer network, then we'd have ML. If we had a 5-layer network, and M. Okay. So we can build bigger and bigger networks. Okay. So you can do your calculations. For every single output, you're adding up over all the previous inputs. And we're going to send each one of those net values through an activation function, which is going to be the output of our perceptrons. Okay. In theory, by Thursday, you'll have all this coded, which matches up to your 2-layer network with 4 hidden nodes. But leave your number of hidden nodes as a variable because you're going to need to change it during the project. But if you can get it coded for 4, in theory, it's easy to change that number. In theory. Okay. I said that we did not have a classifier because we didn't know the weight values. The weights are just random numbers at this point. The files I put up on Canvas, and they are up there since last night, the files that are up there just give you a network. It doesn't give you a classifier, it just gives you a network. And I said in the previous lecture that if we have a linear activation function or no activation function, that we wind up with a series of linear equations. We can use linear algebra to solve for those weights, which is great. But you only get one layer with that because you put multiple layers together, it condenses. Mathematically, it's all the same. Those weights just all merge. So we decided that having this nonlinearity activation function allows us to get multiple layer networks. However, it means we cannot do that linear algebra. So we need an alternative form for how to find those weights. We call that training the network. We start with something that's just total chaos and random numbers, and we build on it. Remington.
Maybe you're having to do with the gradient descent.
The training process has to do with gradient descent. The linear output is just the older, prehistoric neural network. They had to start someplace in the 40s, 50s, and 60s. And they did. And they made progress. They didn't make a lot of progress, but they didn't have the computers we do. And they were trying to figure it all out. So again, a close-up view of our input to hidden nodes. Got all the different weights there. We've got our activation function, which has a summation inside of it, or the net J inside of it. Outputs look just the same, but the number of them that we have depends on how many hidden nodes we had going in and what we're adding in instead of being X's or Y's. Your code should look very similar for each layer. And some of you will do fancy coding stuff that you'll reuse some code from one to the other, depending on how you set things up. So during training, we want to build our weights such that the output, Z is our output, we're going to use Z, not O, is equal to T, which stands for target value. If we do it right, our output will equal our target. Our ZKs will equal our TKs. If we do it right. You're all going to do it right. Nod your heads and promise me you're all going to do it right. So then comes the question of how do we get there? We said we're not going to use linear algebra because we don't have the linear part there. So with something nonlinear, we're going to build a cost function to say how much error, how much wrong are we? We want to minimize the wrong. Because our goal is up there at the top, ZK to be equal to TK. So therefore, our cost is the difference between them squared. It could be an absolute value, but absolute values have a hard time with derivatives, and we're going to use gradient descent, which I introduced a couple classes ago. So we're going to use squared instead of absolute value. And there's a half outside. Any idea why that half might be there? Mumble again? When you take the derivative, that 2 cancels out. And we don't have this 2 floating around. Because 0 is 0 anyway. So we put that half in there strictly so that the calculations, we don't have to worry about that stupid 2 floating around in there when we take the derivative. Has absolutely no other value than to make our math easier. And all of you should like nice math, easy math. We haven't taken a derivative yet. We're about to do so. I'm warming you up as to why we're going to take a derivative and of what we're going to take a derivative. It's coming. But students get all panicky when I start putting derivatives on the screen. I don't want you to panic yet. Not yet. We're getting closer to derivatives. Gradient descent, that's telling you that a derivative is coming. Hold on to your seats. In the gradient descent, we change our weights by our step size. And there's that derivative, the gradient, about how much our cost is relative to what we're trying to find the value for, which is our weights. And we write that gradient with an upside down triangle symbol. And W is our weights. And so each individual weight, and I'm using PQ instead of JI or KJ to represent anything, is going to be looking at each weight individually. So rather than taking all the weights together, let's break it down and look at one weight at a time. So what is that gradient? Hold on to your seats. There's that derivative. Okay, nobody's fallen off your seats. How are the people at home doing? Thumbs up from home? Everybody doing okay at home? How you doing at home? You're doing all right? Leslie's doing fine. Nobody totally panicked when the derivatives came out. Hold in there. We're going to start with the outer layer, weights KJ. And we're going to use chain rule. Remember chain rule? I know you used it a little bit last week. And we're going to take our cost function, and we're going to break it down into the derivative of our cost relative to our output relative to our net, and our net relative to our weights. Our cost relative to our output relative to our net relative to our weights. Simple product or simple chain rule. Simple chain rule. So let's look at our cost function. So remembering your cost function, if we take the derivative with respect to zk, we got that 1/2. We get the 2 from the squared. Our object usual squared, the derivative of x squared is 2x. And then a -1 for our zk. Oops, I wrote this the other way. Okay with the math? So that's the first part of this big gradient. Second part of our gradient. Oh, and it's a summation there, and the summation goes away because if we expand the summation, when we take the derivative with respect to z1, all these other guys go away. When we take the derivative with respect to z2, all these other guys go away. So there is, even though there's a summation in our cost function, it goes away when we do our derivative because that summation breaks out and we're only taking derivative with respect to one of those terms. For our second term, it's going to be looking at the fact that we have z is equal to f net. Our z is equal to f net. Z is equal to f net. So the derivative of z with respect to net is f prime. Whatever that activation function is, the derivative of it. Okay. We took our original gradient, broke it into 3 parts, just calculated the first part, calculating the second part. And the third part, net is equal to the sum of the w's and the times the y's. And so we take the derivative with respect to the weight, all we have left is the individual y. We're taking the gradient, we're trying to update these weights in our output layer relative to our cost. We're breaking the cost into the derivative of the cost to the output, output to the net, net to the weights. We wind up with 3 components. Our total cost, we want to find gradient descent for our total cost. So we're going to take the gradient with respect to z, the z derivative with respect to net, the net derivative with respect to weights. Cost relative to weights is the partial of our cost to our outputs, partial of our outputs to our net, partial of our nets to our weights. Chain rule. And we can calculate each of these 3 different gradients. For everybody but Creston, they're in color so you can see where they come from. So to get this total thing, we just take this, multiply it by this, multiply it by this. We're then going to use the gradient descent by saying we change our weight values by some step size. Remember, we went through all the stuff with skiing in the mountains. Some step size, how big of a step? In the direction that reduces our cost relative to all the possible weights. Which way am I going to go? Which way is downhill? That way. So we have our step. We got all those 3 pieces up there. And this is how we update our weights. So you start with an initial weight. We're going to change that weight value by that much. It's not that badly written, but it is still a little bit ugly. There's lots of pieces in there. So engineers over time have said, let's write things a little bit prettier. And so they've taken this stuff and said, let's call that stuff delta K. It's just a simpler name. And therefore, our update equation then looks a lot prettier, a lot simpler. It's not mathematically any different, but it makes your code simpler, code prettier. You have to do things in a couple of steps, but it's easier to keep track of. And if it's easy for you to keep track of, your code will be neater. And if your code's neater, it might work. Right? You guys have coded enough here. Messy code quite often contains bugs that you can't find. If you can't find your bugs, you can't fix them. And then because they gave it a different symbol, they gave it a name of sensitivity. It's just talking about your steps down. Which way, how much, how's it going? And it's a function of your target value, your output of your net, what your net's giving you, what your neural network's giving you, the stuff you're calculating in homework 5, and what numbers are coming out of those summations that are just before the output. Remington.
So the sensitivity is the gradient descent slope?
Sort of, it's part of your slope. It's just a kind of, it's the name they gave it. No. Yes. No. You're going to update the first set too, but if you can't understand this, you're not going to understand the next part. We're going to get to the next part in a couple of breaths. I'm waiting for you guys to absorb. These are posted on the web. Still, you got to absorb and see what it is that's posted there. You do have to do this at home, kids. So this is what we tend to implement Let's take a look at that. You've got your network. You got this stuff here coded. We'll assume that you finished homework 5. Pretend with me, okay? You finished homework 5. You have this coded. It's part of this bigger network. We're just talking the stuff over here. Each one of these, 10 of them, you've got them all coded. They're in your code. They might not look like that because you might have used some matrix multiplication to get there. Where is it? There we go. But you've got each of these things coded. So you know if I present an A, how many training points do you have? How many total training points do you have? How many is in train.dat? 100. So the first one there is an A. You're going to present eventually all of them. If you present an A, you know what your secret code is for A, and what that code value is for the first output, second output, third output, down to your 10th output. Each one has a value, a number. And when you put in that A, your network is going to give you an output value Z at the first node, second node, third node, all the way down. Along the way, you calculate net K, and I encourage you to save that to a variable someplace because you're going to need to use it. But you have a net K value. You have weight values, starting with the ones I gave you, but eventually you'll update and they'll change. But you have them, they're in a variable someplace. Don't throw it away after you use it. It's still got to be there. And because you did the stuff earlier, you also have Y values. The Y values that came out of the first layer. You've got all these stuff calculated. You have all these Ys, you have all these nets, you have all these Zs, you have all these Ts. These numbers will be different for the first A than they are for the second A, than they are for the 10th A, than they are for the first C, than they are for the Zs. Every time you put a new one in, you're going to get new Ys, new nets, new Zs, and the Ts will change when you switch from A's to C's to E's. And every time you give it one, you're going to be able to get a value for delta K. How many delta Ks do you have? Sort of 100, but that's not really what I'm looking at. You've got 10 output nodes. So you're going to be, for everything you put in, you're going to always get 10 different delta Ks. You got 10 output nodes. So you're going to have K is going to run from 1 to 10. Your TKs, you're going to run from 1 to 10. Your ZKs are going to run 1 to 10. Your net Ks run 1 to 10. So you're going to get 10 different delta K values for every input. When you give it the first A, you're going to get 10 different delta Ks. When you give it the second K, the second A, you're going to get 10 more delta Ks. And each time you can combine it with those Y values to update those weights. And how many second layer weights do you have? How many WKJs do you have? 10 by 4. 40 of them need updating by 40 little equations. If you do things in vectors, you can do an outer product. 2 for loops work. You've got 40 of these guys, 40 WKJs you need to update. For every letter. You show it an A, you're going to make 40 updates. You showed an M, you're gonna make 40 updates. You showed an S, you're gonna make 40 updates. Remington. Vectors and matrices are kind of the same thing. Vectors are matrices where one of the dimensions has only one element, is only one. In your code, depends on your language, whether you code them the same. Usually it's a two-dimensional array versus a one-dimensional array. Two-dimensional array for a matrix, one-dimensional array for a vector. Sometimes the coding cares, sometimes the coding doesn't. But a matrix will have two addresses, one for row, one for column. A vector usually only has one address for which element in that thing, because you know the other one is one. So we've got all the different pieces here. We can do our updating. Okay. Yes, we do have to update the first layer of weights as well. And so similarly, our cost function relative to those input weights, first layer weights, needs to be minimized. So we're going to take a derivative again. Hold on to your seats, more derivatives. You can do it. Again, chain rule. Derivative with respect to our y's, y with respect to our net j's with respect to our weights. Just chain rule. We take our cost relative to our y's. Whoops, there's no y's in that equation. Hang on there, we're okay. We take the derivatives, we know that there's a y embedded in this z. Right? So it's the derivative of that with respect to z and z with respect to y. Well, the derivative of z with respect to y, again, chain rule, is z with respect to net k and net k with respect to y. Hear a sigh in the audience. It's not that bad. The derivative of z with respect to net k is just the derivative of your activation function evaluated at that net k value. Derivative of your net k with respect to y is just your weight. And this time we do need the summations because we look at all of this, any particular zk is going to be built from all these different weight j's are coming into all these different ones here. So we do need that summation this time because all of these things here depend on all of these, because all of these combine in general to all the net k's, net j's. Then our second term is our derivative of our y with respect to our net j. That's just our activation function derivative, slope of our activation function, evaluated our net j value. And then our derivative of our net j with respect to our weights. And that's just our x. Same thing as we had up here before. Put them all together. Not too bad, but it looks a little bit messier than we did on the outer layer. We want to clean up our code. So we're going to take this messy guy. Remember, we had defined the sensitivity term earlier, this delta K. Okay, well, there we go. There's some delta K's sitting there. Okay, take these two terms here. We can replace these two terms. Come on. It won't go away when you want it. It goes away. Can't bring it back. These two terms become your delta K. Okay, it's a little bit cleaner now, but still kind of messy. But we can define a delta J, which looks pretty similar to this. Got that F derivative. It's got our, instead of having our error difference, it's going to have the summation of our output weights and our delta Ks. So we're going to take all of these pieces and define that to be delta J. And that's a lot easier, a lot prettier. And the nice thing that we like from that is it now mirrors what we had before in our outer layer. We like to have things that are, you see the same thing over and over again. So our weight update is going to be that same sort of thing, eta times x times delta I, whereas our other weight update was eta times y delta j. And it's all that information there. And that's going to tell us how much, again, we're trying to update all those weights. How many WJIs do we have?
Will be 4 times like this.
4 by 8, 32.
Oh, this is the second one.
WJI, we're on the input. So we're going to have 40, we're going to be standing at 40 different places. And every time we're going to figure out where are we? How are we going to get down? And we're all going to do this all in parallel. So we've got our 40 WJIs, or sorry, our 32 WJIs and our 40 WKJs. And we're going to think of these as 72 mountains. They all have 72 skiers skiing downhill at the same time. All of them trying to get down at the same time. And if they all come down together, it's good. Okay, they're all going to work as a team, whole ski team out there, 72 people on the ski team, all trying to get down. They're all going to come down. They're not going to leave anybody up behind.
Make sure we make 32 updates for every data point.
We have 32 different, yes, we're going to update 32 variables. When we show it in A, going to update 32 variables. When we show it with a C,
That's like always a big one for me. We'll make 18 things.
plus the 40 updates from the previous for the other layer.
So I'm gonna add it. But is this supposed to be J instead of I?
No, because we're now updating WJI. When we were updating WKJ, then it was K and J.
No, I and I should be I and J.
Oh, sorry, the X. Yes, you're right. Okay, that should be a J.
And then the next line as well.
Trying to type these up for you guys rather than write on the board. Okay. So you're ready to go off and do the project, right? No. But I want you to think about, what do you have? What are you going to be needing to do? You've got your network, which we're going to pretend you all have finished today, and you will have it finished by Thursday. And as you code this, you've got all those different variables you're calculating. So you're going to make sure those variables exist. Don't skip steps because you need them all. You could immediately calculate yj from xi and wji, but you need that net j value later on, so calculate it. Don't put them into one statement because you need that net j value. So all those different labels up there, you need all of those variables. As you code going forward, you need each of those variables. Then you're going to add it additionally and make a variable called delta k by taking a tk and then subtracting from it your zk, taking the derivative of your algebraic function and putting in your net k. So you've got zk and net k when you go forward. And after you reach the end, you finish homework 5, you're going to take those values after homework 5 and calculate delta k from those extra variables that are hiding around in your network when you do homework 5. Then you're going to take your other values and you're going to take your delta k values, your output weights, your net j's, and you're going to calculate some delta j's too. So you do homework 5, you get all those variables, put a break in your code, then you're going to calculate delta k, then you're going to calculate delta j, or at least have code ready to do that. And then with delta k and delta j, you can update your weights by this amount or this amount. So you need to have an eta value floating around someplace. We'll get to that. So you do homework 5, calculate delta k, calculate delta j, calculate change in weights kj, calculate change in weights ji, then change your weights. Come back to the beginning of homework 5, do the whole thing again with your new weights. Change your weights. Then you're getting a homework 5, do it again. A little bit, starting to come together, starting. You don't need to have 100% right now, but you can sort of see what we're doing. You had a question in the back? Which slide? 40? 3.
Down we have theta xi delta j. Could you swap the xi and delta j and then do an outer product to make that a little bit simple?
Yeah, how you do it is fine. Yeah, you can do 2 for loops or you can do an outer product, depending on how you want to code. Okay. What does that equal? A row vector 3, 2 times a column vector 5, 4. From all your expertise in linear algebra, if I reverse the order of those, column vector 5, 4 times row vector 3, 2. Talk with your neighbors. Talk with your neighbors so you all get it. Some of you know more linear algebra than the others. Yeah, that's a 3, 2. Some of you know more linear algebra than the others. It is different than the first one. So what do you get? 15, 10, 12, and 8. You wind up with a matrix. This is a dead pen. Story of my life here. This first one is an inner product of two vectors. The second one is an outer product of two vectors. So here, what are we trying to create? A matrix. So we want to use an outer product. So use X as a column vector and delta as a row vector. And you can do it in one step. Eta is a scalar. Doesn't matter. Doesn't matter which order you define them, but you need an outer product if you're going to do it as a matrix. Or you can put it in 2 for loops. Your code, figure out what you like. Usually X we write as our input as a column vector. But you can do whatever you like. Your computer will probably get upset with you if you wind up with something where the dimensions don't match. Okay. An inner product is also sometimes called a dot product. You may have heard about in some math class eons ago. And there we usually think about looking there, we're going to take those products, 3 times 5, 4 times that, and add them. But it's the same thing. And then, of course, you know that the dot product of 2 vectors is your cosine of your theta. All that other stuff that you once upon a time learned and didn't know why they were teaching it to you. And they were teaching it to you because they knew eventually you'd take a machine learning class and you would need it. Right? So you can go back and tell your high school math teacher, thank you, you needed it for your machine learning class. Okay? So big picture, we'll get into more details next on Thursday. Project 5 or homework 5. There we go. We get to go from X to Z. You're then going to show it a particular X for like your A. And you know what your target is for an A. For now, we'll say 1, 0, 0, 0, 0, 0. From there, you can get your difference. You knew your net K that was there. You have the derivative of this. You get your delta K. You can update your weights. Create your delta J, which you combine there, multiply by your Y. Your delta J is made up of your nets, which then can update your weights here. And we can show it another character and go forward again with some new weights. Give it your A, calculate your nets, calculate your Y, calculate your nets, calculate your Z. You know your T, you get your difference. Combine your difference with your nets and your weights and your Ys and your nets. You update those weights too. These backwards arrows are called back propagation. The algorithm of back propagation. You're not doing that in homework 5. You are doing that in project 3. Homework 5 is just going forward. Because you can't go forward. There's no way it snowballs chance you're going to make it backwards. So let's make sure you can go forward by Thursday, all of you. We will go through it again on Thursday. I won't go through the derivation. We've already done the derivation, but we'll talk about more of the big picture, the pieces that come in there. Right now, I want you to have kind of that big fuzzy feeling. Homework 5 goes forward. Back propagation is using that error to get your delta K, which combines with your Y, J, to update your weights, WKJ. Then you can build your delta J, which combines with your inputs XI to update your weights JI. Now you have a new network to do homework 5 again. Calculate all your different things, keep changing your weights, new network, go forward again. How many times do you do this? Till you get decent results. Gradient descent. What are your 3 stopping conditions for gradient descent? Maximum iterations at your emergency stop. Is your error close enough? Your error small enough? Your change, you've reached the flat area, it's time to hike. You're no longer skiing downhill, you're on that flat stuff by the ski lodge. You're not making any updates, it's just, you have to start working. And that's the same thing with your network. You start with some initial weights. I gave you some initial weights. Build your network going forward. Then you make those changes to your weights by using those variables backwards. You got new weights. Bring your network going forward. Are we done yet? Do our Z's equal our T's? Probably not the first time. Okay, have we exceeded our number of steps? No, you're going to do it more than once. Okay, we're not down yet. Change all of our weights. Got new weights, show it a letter. Bring it forward. Is our error good? Probably not yet. Change your weights. Show it another letter. Is our error 0 yet? Close to 0? Change your weights. Until you've done this so many times, you just want to say, I'm done with it. And that should not be where you want to stop, but have your emergency off. Or your error's really low. Or you're not making any changes. Those weights have not changed much. That gradient descent process. You now have all learned backpropagation. How many of you had heard the term backpropagation before here? Just a couple of you. Okay, it's a very big keyword in neural networks. My hope is that when you finish project 3, you'll have a very good understanding of it. And then we'll build into how does that then apply to these deep learning neural networks, which are the same thing on steroids. Why could they do it on steroids? Computing power got bigger over the years. So the very, very first time that backpropagation came out was in the early 80s. It was actually invented earlier than that, but they didn't realize it applied to this. And then they're like, hey, cool. Finally, this problem, we can no longer use linear algebra. We can do this backpropagation. We got it. Hey, you know, we can do this. You know, we can do this. Hey, we can do this. And everybody's jumping up and down, all excited. Papers everywhere. Neural networks, they're going to solve all of our problems. And that lasted about 5 years, 10 years, maybe. And they said, yeah, well, sometimes it works, but it doesn't work really well. Go back to other things. And then literally what happened, I'll give the secret away, we'll quit, is that there was a professor who had a PhD student, which is a good way to get a lot of work done, have good PhD students. Remember, we talked about how you do a 2-layer and turn it into a 3-layer, and you could turn a 3-layer into a 4-layer, or into a 5-layer, or a 6-layer. And the professor just kind of said, well, you know, just add more, go play, and you know, train it. Well, the training time saying, well, keep running it overnight. Let's just keep letting it run. And so the professor, because it didn't have time to deal with the grad student, just said, you know, build a deeper network, just let it run. I don't, you know, come back to me next week. I'm busy. I can't talk to you right now. And so this grad student had built this really deep network and didn't just hit that emergency off button. He let the stupid thing run for weeks. Came back and looked at it and was like, hey, wow, the error, it's really, really low. It worked. And he went to see his professor, and the professor, what are you bothering me about? What do you got? And that's when they realized they could do some other things. There's a few other things that came into play too. But it literally came about from a grad student to the professor saying, build it bigger and just let it run. I can't answer you today, just let it run. And that's when, with the new computing power, he was able to do something a little bit more than they could do in the 80s. When I ran a neural network project for a course similar to this in the late 80s, early 90s, I went into a computer lab of Spark stations. They were pretty good end computers. And I ran one case on each of the different computers, on about 5 different computers. I logged into 5 different computers and ran it and just sat there and did something else for half an hour to an hour waiting for things to run for just small networks. These will not run fast. Okay, that's all for today. We'll do more exciting things on Thursday.